Section: Introduction. In this section, we discuss how one of the most remarkable achievements in artificial intelligence was when IBM's Deep Blue beat the world chess champion Garry Kasparov in 1997. This event was a big deal because it showed that machines could beat humans in activities that require deep thinking and strategic planning, which were once thought to be unique to humans. Deep Blue was a special kind of system that used a huge amount of chess knowledge and smart strategies, along with a powerful method for looking ahead in the game, known as alpha-beta pruning. Today, most of the top chess programs use a similar approach, with Stockfish 16 being the strongest one that people can use. However, there are exceptions like DeepMind's AlphaZero and its open-source version, Leela Chess Zero, which learn strategies on their own without using human chess knowledge and are also very strong competitors. Lately, there have been big advancements in AI that have improved how machines understand and interact in areas that were tough for older systems like Deep Blue. These improvements come from using general methods, especially training machines using a lot of data where they learn from examples, and using special models that pay attention to important parts of the data. This has led to the creation of large language models, LLMs, that can do some pretty surprising things, like those made by OpenAI and Google DeepMind. However, it's not clear if these methods would work well for chess, where you often need to use complex reasoning and detailed strategies. So, we wanted to find out if we could teach a machine to play strong chess without having it plan moves ahead in time. To do this, we used a lot of data to train a model to predict the best moves in chess. We based our predictions on how likely they were to win the game. The quality of our chess playing strategy depends entirely on how good our model is at making these predictions. To get a lot of accurate data for training, we used Stockfish 16 to evaluate millions of positions from games played on Lichess.org by a wide range of players. Our results showed that we could create a chess playing strategy that plays at a Grandmaster level, as shown by its performance against humans and in solving complex chess puzzles. This strategy even performed better than some of the most advanced AI models and AlphaZero in terms of chess ratings. Our main contributions are that we managed to create a model that can predict chess moves very well, leading to a high-level chess-playing strategy without needing to plan moves ahead. This strategy can play against humans at a Grandmaster level and solve difficult puzzles. To our knowledge, this is the strongest chess engine that doesn't need to look ahead in the game. We also showed that getting good results depends on using a lot of data and a sufficiently large model. For the methods, we explained how we gathered our data, created our predictions and strategies, and how we tested them. We downloaded 10 million games from Lichess from February 2023 and analyzed all the positions in these games. We used Stockfish 16 to estimate how likely each position was to lead to a win, and we did the same for all possible moves from those positions. This gave us a lot of data on which moves are likely to be the best. We also made sure to include a variety of games and shuffled the data to avoid any biases. For testing, we used a similar approach but with games from a different month and also created a set of chess puzzles to see how well our model could solve them. Section Summary. In this section, we distilled an approximation of Stockfish 16 into a neural predictor through supervised training on a large dataset from Lichess games. By predicting action values for chessboards without explicit search, our resulting chess policy achieved Grandmaster-level play, Lichess Blitz LO 2895, and outperformed GPT 3.5 Turbo Instruct and AlphaZero's networks. This work demonstrates the possibility of using standard supervised learning at scale to develop a strong chess engine without the need for explicit search, showcasing the potential of neural networks in strategic decision-making tasks. Section: Value binning. In this section, we discuss how we prepare our data and design our model for predicting outcomes in a game setting. We start by explaining the process of value binning. Since the predictors we develop are meant to classify data into discrete categories, we need to transform win percentages, which are continuous values, into discrete classes. We do this by dividing the range from 0% to 100% into uniform segments, which we refer to as bins. Each bin is then represented by a unique one-hot code. Unless we specify otherwise, we use 128 bins for this purpose. In experiments where we focus on mimicking the choices of an expert player, known as behavioral cloning, we predict actions that are already discrete, so this binning process is not necessary. We also explore how changing the number of bins affects our results in a specific section of our experiments. For the architecture of our predictors, we utilize a modern transformer model that is designed to work with sequences of data. This transformer model is adjusted to output discrete probabilities by applying a normalization process known as log softmax to its outputs. This means the model gives us the logarithm of the probabilities for each class. The size of the input that the model can handle is set to 79 tokens for predicting the value of actions, and 78 tokens for predicting the value of game states and for behavioral cloning tasks. The number of output classes matches the number of bins for value predictions, and it is set to 1968 for behavioral cloning, which corresponds to the number of all possible legal actions in the game. We ensure our model can understand the order of inputs by using learned positional encodings, as the length of our input sequences is fixed. Our largest model configuration contains approximately 270 million parameters, and we provide detailed information on how model size affects performance in another section of our experiments. When it comes to representing the game states, we use a format known as FEN, which is a concise string representation of a game board. We convert these FEN strings into fixed-length strings of 77 characters by converting each character into a token based on its ASCII code. If necessary, we pad these strings with spaces to ensure they are of uniform length. It's important to note that we always represent the board from the perspective of the player whose turn it is to move, without flipping the board's orientation. For actions, we use a notation called UCI and assign each possible action a unique token based on its position in a sorted list of all legal actions. Our training process involves minimizing a specific type of error, known as cross-entropy loss, through a method called stochastic gradient descent with the help of an optimizer named Atom. We train our models for 10 million steps, which is equivalent to about 2.67 epochs given our batch size and the total number of data points we have. Depending on the task, our models are trained to predict either the correct bin for value predictions or the correct action for behavioral cloning, using a one-hot encoding approach for the labels. Finally, we describe how our predictors function. They are essentially neural networks that take tokenized inputs and output a probability distribution over the discrete classes or actions we've defined. We differentiate between three main tasks: predicting the value of taking a certain action, predicting the value of a game state, and mimicking the actions of an expert player. For action and state value predictions, we calculate the loss based on how well the model's predictions match the actual bin corresponding to the true value. For behavioral cloning, the goal is to accurately predict the action taken by the expert in the same situation. Section Summary. In this section, we discretize win percentages into classes using value binning by dividing the interval between 0% and 100% into k-bins. We utilize a decoder-only transformer backbone to parameterize a discrete probability distribution for predicting action and state values, with the model outputting log probabilities. The training protocol involves minimizing cross-entropy loss via stochastic gradient descent using Atom over 10 million steps for predictors that are discrete distributions parameterized by neural networks. Section: Evaluation. In this section, we discuss how we evaluate our models to compare them with each other, track their training progress, and measure their effectiveness. We use four main metrics for this purpose. The first two metrics focus on assessing the accuracy of our predictions, while the last two are about evaluating the performance of the policies derived from these predictions. Firstly, we look at action accuracy, which is essentially the percentage of times our model's suggested action matches the best action as determined by the ground truth in our test set. This is a straightforward measure of how often our model makes the right choice. Next, we consider action ranking, which involves using Kendall's rank correlation coefficient. This statistical measure helps us understand how well the order of actions predicted by our model aligns with the true ranking provided by Stockfish, a highly regarded chess engine. The correlation values can range from -1, indicating an exact opposite order, to 1, which means the predicted order perfectly matches the ground truth. A score of 0 would mean there's no correlation at all. For the third metric, we use puzzle accuracy to evaluate how well our models can solve chess puzzles. These puzzles vary in difficulty and are rated using an ELO system, with ratings ranging from 399 to 2867. The accuracy here is determined by the percentage of puzzles where the sequence of actions taken by our model exactly matches the known solution sequence. For a detailed analysis, we use a set of 10,000 puzzles, but for quicker evaluations, we limit the set to the first 1,000 puzzles. Lastly, we assess the game-playing strength of our models using an ELO rating system. We do this in two ways: by having our models play blitz games on Lichess against either humans or bots, and by organizing an internal tournament among our models, excluding GPT 3.5 Turbo Instruct. We play a significant number of games to ensure reliability in our ELO ratings, which are calculated using the Bayes ELO system. To make the games more varied and prevent predictable outcomes, we introduce some randomness into the decision-making process of our models, especially during the initial moves. In addition to these evaluation metrics, we compare our model's performance against several baselines, including Stockfish 16 and different variants of AlphaZero, as well as GPT 3.5 Turbo Instruct. It's important to note that these baselines have access to the entire game history, unlike our models, which only consider the current state of the game. This difference in information availability is significant, especially in dealing with certain chess rules like the threefold repetition draw. Our results show that our transformer models, which vary in size, all demonstrate the ability to generalize well to new situations and solve a substantial number of puzzles. Larger models consistently perform better across all metrics, confirming the importance of model scale for achieving strong chess performance. Our largest model achieves a Blitz ELO rating that places it within the Grandmaster level when playing against human opponents, although its performance slightly decreases against bots, likely due to differences in the player pool and other factors. In summary, our comprehensive evaluation demonstrates the effectiveness of our models in playing chess, with larger models showing superior performance. However, we also discuss potential limitations and areas for further investigation, particularly regarding the differences in playing against humans versus bots. Section Summary. In this section, we evaluate our models using various metrics to compare their performance and measure training progress. We assess predictors based on action accuracy and action ranking using Kendall's correlation, while policies are evaluated on puzzle accuracy and game-playing strength measured in ELO ratings through blitz games and internal tournaments. Our large-scale transformer models demonstrate non-trivial generalization to new scenarios, with larger models consistently showing improved performance across all metrics, highlighting the significance of model scale in achieving strong chess performance. Section: Puzzles. In this section, we delve into the intriguing world of chess puzzles to evaluate the performance of our model, which boasts 270 million parameters, against formidable opponents such as Stockfish 16, GPT 3.5 Turbo Instruct, and AlphaZero's value network. We meticulously selected a large set of 10,000 puzzles, each categorized by their difficulty level as determined by the ELO rating system on Lichess. Our findings reveal that Stockfish 16 outshines all competitors across every difficulty level, with our model securing the second spot. Both AlphaZero's value network, which was trained on 44 million games, and GPT 3.5 Turbo Instruct show commendable puzzle-solving capabilities but fall short of matching the prowess of our model. It's important to note that solving these puzzles requires not just any move, but the correct sequence of moves. Since our policy doesn't plan moves ahead in a traditional sense, success hinges on accurate value estimates that guide decision-making one move at a time. Moving on to the topic of scaling laws, we conducted an analysis to understand how the size of the dataset and the model architecture influence puzzle-solving accuracy. This analysis, depicted through graphs, shows a clear correlation between puzzle accuracy and both the size of the training dataset and the architecture of the model, which also reflects in the overall playing strength. When training with a smaller dataset of 10,000 games, we observed that larger models with more than 7 million parameters tend to overfit as training progresses. However, this tendency diminishes when the dataset size increases to 100,000 and further to 1 million games. Our results consistently demonstrate that larger datasets lead to higher final accuracy across all model sizes. Moreover, increasing the architecture size generally boosts performance, regardless of the dataset size, confirming the trend observed in our main findings. We also explored various experimental variants and conducted extensive ablations using a model with 9 million parameters. The outcomes of these experiments informed our decisions regarding the default configurations for our model, data, and training processes. One key area of our investigation was the choice of prediction targets. By default, our model predicts action values based on the current board state. We compared this approach with alternatives, such as predicting state values or mimicking expert moves, behavioral cloning. Our experiments, summarized in our results table, show that predicting action values leads to superior performance in ranking actions, action accuracy, and puzzle-solving accuracy. This advantage likely stems from the larger dataset of state action pairs available for action value prediction. To further validate this, we conducted an additional experiment where all 3 prediction targets were trained on an identical amount of data, which largely supported our initial hypothesis. Lastly, we examined the impact of increasing the depth of the transformer network while keeping the total number of parameters constant. Our findings suggest that performance improves with network depth but plateaus around 8 layers, indicating that while depth is beneficial, there's a limit to its effectiveness. Additionally, we experimented with data sampling methods to enhance the diversity of our training and test sets by removing duplicate board states. Comparing a weighted data sampler, which mimics the natural distribution of board states, with uniform random sampling from our filtered dataset, we found that uniform sampling leads to better performance. This suggests that the increased diversity and reduced likelihood of memorizing early game positions contribute to the improved performance of our models. In summary, our exploration into puzzles, scaling laws, and various model configurations has provided valuable insights that have shaped our approach to developing a competitive chess-playing model. Section Summary. In this section, we compare the puzzle performance of our 270M parameter model with Stockfish 16, GPT 3.5 Turbo Instruct, and AlphaZero's value network using a large puzzle set grouped by LO difficulty. Stockfish 16 performs the best across all difficulty categories, followed by our model, while AlphaZero's value network and GPT 3.5 Turbo Instruct lag behind. Additionally, we analyze the scaling of puzzle accuracy over dataset and model size, showing that larger architectures tend to overfit with small training sets but lead to increased performance as dataset size and architecture size grow. Section: Value binning. In this section, we discuss the process of value binning, where we explored the effects of using different numbers of bins for discretizing state and action values, ranging from 16 to 256. We found that increasing the number of bins generally leads to better performance. To find a middle ground between performance and computational efficiency, we decided to use 32 bins for our preliminary tests and 128 bins for our main experiments. When it comes to the loss function, we approach the learning of Stockfish action values as a classification challenge, aiming to minimize cross-entropy loss, also known as log loss. This method aligns closely with the standard setup used in large language models, LLMs. Alternatively, treating the problem as a scalar regression and minimizing mean squared error, which is equivalent to optimizing a fixed variance Gaussian likelihood model with a transformer, was considered. However, we found that log loss performs better than mean squared error in 2 out of 3 metrics we evaluated. Regarding the Stockfish time limit, we generated training sets from 1 million games annotated by Stockfish under various time limits to adjust the playing strength of our reference system. We observed that a minimal time limit of 0.05 seconds only slightly reduces puzzle performance. Therefore, we chose this as our standard setting, which requires about 15 billion action evaluation calls with Stockfish for our dataset of 10 million games, equating to approximately 8,680 days of Stockfish evaluation time without parallel processing. In the context of related work, early chess AI research heavily relied on explicit search strategies and heuristics, as seen in Turing's initial experiments and implementations like NeuroChess. This evolved into systems like Deep Blue and Stockfish, which are known for their advanced search algorithms. The introduction of AlphaZero represented a significant shift, using deep reinforcement learning, RL, with Monte Carlo tree search to learn heuristics instead of manually creating them. Neural networks have become increasingly important in chess AI, enhancing self-play mechanisms in AlphaZero, employing deep RL, and moving away from explicit search methods by using large-scale game datasets. The emergence of large language models has also brought innovations in chess AI, including language-based models, natural language encoding of chess games, and evaluating the ability of LLMs to play chess. Recent studies have shown that strategic input representations and value loss enhancements can significantly improve the chess performance of vision transformers, and incorporating chess-specific data sources into language model training can enhance their performance in chess. Research on scaling effects of transformers on chess performance aligns with our focus on the significance of model and dataset scale. Lastly, we address two technical challenges in using our state-based policies for playing against humans and bots due to the lack of access to game history. One issue is blindness to the threefold repetition rule, which we mitigate by adjusting the win percentage to 50% for moves that would trigger this rule, although our bots cannot plan to avoid threefold repetition. Another challenge is indecisiveness in situations of overwhelming victory, particularly when Stockfish detects a mate in K situation. We map these outputs to the maximum value bin, leading to potential randomness in our agent's play in strong positions. To counteract this, we ensure that if the predicted scores for the top 5 moves are above a 99% win percentage, we consult Stockfish to choose the top move for a consistent strategy across time steps. Section Summary. In this section, we explore the impact of varying the number of bins for state and action value discretization, finding that more bins enhance performance. We opt for 32 bins in our ablations and 128 bins in the main experiments to balance performance and computational efficiency. Additionally, we train Stockfish action values as a classification problem using cross-entropy loss, which outperforms L2 loss in 2 out of 3 metrics according to our ablations. Section. ELO. Humans versus bots. In this section, we discuss the differences observed in ELO ratings when our bots play against humans versus when they play against other bots on Lichess. We've noticed that our bots tend to have different outcomes depending on the type of opponent, and there are a few reasons we believe this happens. First, humans are more likely to resign when they see that our bot has a high chance of winning, something that many bots won't do. This amplifies the issue when our bots face off against other bots. Second, since humans rarely play against bots on Lichess, comparing the two groups, humans and bots, is challenging, and the ELO ratings might not accurately reflect the true skill levels across these groups. Third, based on some detailed, though anecdotal, analysis by a chess national master, we've found that our models sometimes make tactical errors. These mistakes seem to be punished more harshly by bots than by humans. While delving deeper into why these ELO rating discrepancies occur is intriguing, it's not the main focus of our paper and doesn't affect our primary arguments. Moving on to the limitations of our work, even though our largest model performs very well, it hasn't yet matched the capabilities of Stockfish 16. Our experiments suggest that with a sufficiently large model and enough data, we might close this gap. However, we can't definitively say that we will achieve this. Another issue is that our predictors only see the current state of the game, not the entire history. This limitation introduces some challenges that we can't overcome without incorporating specific heuristics or adding more data and observable information. Additionally, when we use a state value predictor to create a policy, we consider all possible future states that can be reached through legal moves. This involves having a transition model and can be seen as a form of one-step search. It's important to note that our predictors don't explicitly search through sequences of actions, but we limit our claim of operating, without search, to our action value policy and behavioral cloning policy. The primary aim of our project was to see if we could approximate the complex, search-based algorithm of Stockfish 16 using a feed-forward neural network. We've made a significant effort to develop a strong chess policy and to estimate its playing strength. However, we haven't explored every possible way to enhance this strength, and it's possible that further adjustments could yield even stronger policies. We've also tried to gauge our policy's strength through Lichess, where it appears to perform at a Grandmaster level against human opponents. Yet, we haven't tested our policy in official tournament settings. Moreover, we can't dismiss the possibility that opponents might find and consistently exploit weaknesses in our policy over time, given its relatively deterministic nature.